SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 8. We were talking about the various factors which were available with the designers, like the variability control factor and the target control factor. I would just like to look at one practical example which has been proposed by Taguchi to sort of separate what is the variability control factor from the target control factor by looking at a transistor circuit. Okay. So let us say there is an electrical power circuit that you are designing in this particular case, and if you look at the quality characteristic of interest, this circuit gives an output voltage Y with the target value, let us say, of Y0. So the target value here is basically Y0 and the output voltage of the circuit is Y, and obviously the output voltage is very largely determined by the transistor gain, which is again plugged into the system in the circuit, and the gain is represented by the parameter X, okay, whose nominal value can be controlled within a certain range or whatever, and the input output relationship of the Y versus X, that means the level of the output voltage versus the gain voltage, is a sort of non-linear relationship as shown in the figure here in the next page here. This is how you can vary the Y, which is the output voltage of the circuit, and this is the transistor gain. Okay, so this is the gain voltage, and you can vary, as you can see, in a non-linear manner, okay, the Y versus the gain voltage X. So this is the transistor gain. And you can actually see here that the product design engineer can select the nominal value of X to be X0 to achieve a target value of Y0. You can see in this particular graph, for example, this is the range of the transistor gain which has been chosen at the first instance by the designer, and that results in an output voltage Y0, as you can see here, which has a large variability. Okay. So large variability. So however, if supposing the obviously the target level was Y0, you have to remember, and the Y0 can only come when you are going equal to this particular transistor gain range of X0. However, as a designer, if you were to operate this circuit at a different transistor gain, let us say at X1, obviously the output voltage here would be much higher. Okay, so output voltage is much higher than the target voltage, which was actually Y0. Okay, so this Y1 apparently is quite higher than Y0. Okay. However, you can see here that the variability level here was very high, but the variability level here, because of the nonlinear relationship between the transistor output voltage and the gain, is reduced a lot. So you can say the variability in the output is reduced. Okay. So the variability here, for example, starts from Y0, let us say lower limit, to Y0 upper limit, which is this and this limit, whereas in this case it is Y1 upper limit and Y1 lower limit, which is this and this limit. So obviously there is a less variation in the range of Y1s in comparison to Y0s. Okay. So I can write this down as variation at gain equal to X1 is much lesser, and this is variation in the output, much lesser then variation at gain equal to x0. So, as a designer you really have to choose how you would like to plan your circuit to operate. Obviously, because the mean value reported here y1 is much higher than y0, you could probably bring a resistive loss component by putting an additional resistance in the circuit, so that there is a drop in voltage and y1 can come to y0. But the advantage you are getting is that the variability at y1 is very small in comparison to the variability at y0, and so obviously it would be a wise idea to put a resistive loss in the circuit, so that there can be little variation in the output, because resistance is by and large a linear part of the circuit, whereas this gain versus output voltage is a non-linear characteristic. So this is how you basically plug in the target control factor and the variable control factor. So in this whole process, you have the transistor gain as the variability control factor, whereas the resistance, or you can say this, the load resistance, is the target control factor. So while the resistance ensures that the output value goes to a certain level y0, which is the desired output value, the gain value actually from a very different angle, from a nonlinear response of the gain with respect to the output, ensures that the variability is closed on. So you will have to understand all engineering systems in terms of that variability control factor and gain control factor. So it is very clear now that a gain voltage variation is resulting in a change in the variability of the output, okay, whereas the resistance, the load resistance, is again tailoring that output back into the target value of y0, which was otherwise intended for this particular power circuit to happen. So the control factors now, transistor gain is the variability control factor, and the load resistance here is the target control factor. So this is how you have to understand and analyze engineering systems. Let us now look at another aspect of the various engineering systems, and we will talk about noise factors, which are highly detrimental to the performance of the system, but they essentially, although they have to be eliminated, but sometimes they are necessary evils which are present. For example, a wear in a transmission is a definite evil which is always going to be there, and you cannot avoid this from happening, and you can say that this is a noise factor. Obviously, there can be a noise which can be related to the external environment of a product, and there can be a noise which is related to the internal nature or characteristic of the product, and then there can be a variability between the different products which are produced across a different production process. So noise factors in general are responsible for the functional characteristics of a product deviating from the target value, and obviously the outcome is a change in the quality loss, an increase in the quality loss, because the target is not being met properly. And noise factors can be classified as outer noise, and outer noise basically means that the variables which are external to a product and that affect the product performance, which is known as basically the external noise factors. Examples can include, let's say, variation in temperature in a paint shop, okay, or humidity in a paint shop, or dust level in a paint shop of an automotive. So this is actually an outer noise which you really cannot control, okay, and you can control by probably developing an environment which is more sort of suitable, but again the environment has to also keep changing based on the outside environment conditions which are determining the final values of this closed environment that you have made around the particular process. Okay, so this is outer noise. Inner noises are basically the variations due to deterioration of the parts of materials itself. For example, you can have a natural loss in resilience of springs as they are subjected to repeated cycles of use because of fatigue or other engineering phenomena. You can have a gradual wearing out of parts due to friction because of multiple usage of the parts while in assembly. And then you can also have an increase in resistance of resistors with age, etc., which is beyond your control, and this is actually called the inner noise, which gets generated because of more number of cycles of usage, etc., of a certain product. So the outer noise is still to some extent controllable, but the inner noise is something which is completely random, and you'll have to design the system in a manner so that this variability is always there, as a part of the systems or the product's life cycle. Okay, and so towards the end of the life cycle of the product, you'll have to accommodate a higher variability in these values than towards the beginning of the life cycle of the particular product. Okay, and then obviously there are noises between the products where there is a huge variation between two different products of the same category in terms of their material characteristics, in terms of their manufacturability. It is basically material variability, etc. So when you are having a production line or a manufacturing unit which is producing many products, there is obviously going to be some variability between the item 1 and item 2 of the same manufacturing process. Okay, so that's called the between product noise, and is quite well illustrated in the linguistically in this whole statement as well. So they are by and large uncontrollable factors, all noise factors, and trying to control these factors may really be a very, very expensive proposition, although it's not impossible to some extent, but obviously you'll have to consider a lot of aspects. Just because they are very random in nature, their controllability becomes a real problem, particularly when you're talking about engineering systems. So by and large, the whole Taguchi's approach of robust designing is based on attempts to reduce the variability by changing the variability control factor while maintaining the required average performance through appropriate adjustments in the target control factors. You've just seen an example problem before of the transistor and how gain is able to influence the variability control factor. Okay, so that is how by and large you should design a system, by studying different parameters related to a system and trying to see is there a controllable basis which you could actually introduce so that the overall variability in the output level reduces. Okay, and you will have to go off the box sometimes, out of the box sometimes, to think, like in the case of the transistor you saw. Okay, so all the engineering systems now have to be classified in this particular manner as the controllable and uncontrollable factors, okay, the signal factors, the response factors, and you have also learnt about variability control factors or target control factors, or then again the neutral control factors, which were at one point of time with the designer, signal factors totally being with the operators and users, and the noise factors which are not really in control of anybody, and controlling them may be a very, very expensive proposition. So this is in general a way of classification of any particular engineering system, and you should be able to now take any engineering system around you and try to classify them based on this concept and see if you could do something out of the box so that the variability of the overall output level reduces. And that could be a design improvement that a person can do on a product, okay, if you want the output level to be at a certain value with a very minimalistic variation as much as possible. Okay, so with this I would like to sort of conclude this round or this module, and I would just like to probably do the next module where we'll intensely work on how to really learn about failure modes and how that affects the system, and then can we really prioritize certain aspects of the system so that we are able to minimize the failures of products as far as the quality basis of the system goes. Thank you so much.